a ton left, so I'm going to back up just a little bit and go back over the calculation of molarity and molality. Those are important, and it's not going to take a whole lot of time to go back over. So we said molarity was the moles of the solute over the liters of solution. You've probably seen through homework and things that a lot of times problems will be given to you in grams of something in a certain volume. And so in that situation, you have to convert your grams to moles, and then you can divide by your liters. But these problems can be in any format. You can be given any two of the three and have to solve for it. Today's quiz is going to be a lot of these in different formats. Maybe given molarity in moles, solve for liters. Given molarity in liters, solve for moles, things like that. Yes?
It's okay. Don't worry about it.
Which example?
Okay. Anything. Like anything.
So in the lab, in a chemist in a lab, a lot of times will say, okay, I need a 2 molar solution of sodium chloride. Okay? And so the question becomes, I need a 2 molar solution. How much do I need? Say I need 500 milliliters. Okay? So I need 500 milliliters of a 2 molar sodium chloride solution. So I have to figure out how much sodium chloride do I need. Okay? So
it has to be in liters, right?
What sodium chloride, a solid, liquid, or gas?
Say it again?
Sodium chloride, solid, liquid, or gas? If it's sitting on a bench in a lab,
That's solid.
it's solid, right? So it's going to be in grams, right?
Okay.
So if you're going to, you have to find out how much sodium chloride you have. You're going to weigh it out in grams. The grams are nowhere here, right? So I know I need 2 molar solution. So 2 molar equals moles over liters, and I said I need half a liter of it. Or I said 500 milliliters,
Yeah.
which is half of a liter, 0.5 liters. So now I now have 0.5 on the bottom. If I solve for moles, what do I get? That's 2 times 0.5. 1. So moles equals 1.0. So then I have to figure out how many grams is 1 mole of sodium chloride. So I can take 1.0 mole sodium chloride. 1 mole sodium chloride is 58 grams. Sodium chloride equals 58 grams sodium chloride.
Okay.
So that tells me to make my solution, I have to weigh out 58 grams, and then I dissolve it in water so that I get half of a liter total. And then I now have a 2 molar solution. So this is the same example we already did. So what am I trying to do? Again. Nobody. You already got the answer. Thank you. Yeah.
It's 2.08.
Fine, 1.04. And you've got 3 seconds. Yeah, that's it. Brandon did the rest.
What?
Brandon did the rest. So he needed moles divided by liters. Liters is directly given to us, 2.0, so he's got 2 on the bottom. To get moles, he just converted 117 grams of potassium hydroxide, 117 grams to moles. Now he has his moles, moles divided by liters is 1.04 moles. We then said, in a perfect world, molarity is best. Molarity is very convenient in the lab. But when temperature changes, the volume is going to change a little bit. And so in some situations, we can't have that happening. We need to know exactly how much solute we're getting out. So if we calculate that we have a 2 molar solution, and we cool down that solution, do you expect the volume to increase or decrease? In general, when things get colder, do they get larger or smaller? They get smaller. So it's not like when we're doing our gas laws, but liquids will shrink a little bit when they get cold. So if the volume goes down, are the number of moles in our solution going to go down with it? No. If I have a beaker of sodium chloride solution, the water is going to contract, but there's not any less sodium chloride in there, right? And the amount of sodium chloride determines this. So if that stays the same and that gets smaller, the molarity goes up. So we said in those situations, we need to use molality instead of molarity. And molality was basically the same calculation, except on the bottom, instead of liters of solution, it was kilograms of solution. So we're not gonna do this example. This is where we left off. Dilutions. Dilution calculations are not hard. This formula is not on your cheat sheet, but it's not all that difficult. M1V1 equals M2V2. So it's not on your cheat sheet, so I would circle it or something in your notes. Just like always, our V's are volume. 1 is before, 2 is after. The M's are molarities. In this equation, we have M for molarities. The same equation works whether it be molality or percent by weight or percent by volume, or anything like that. In some situations, if you look this up online, you may see it as C1V1 equals C2V2, where C is concentration. And you can plug in whatever unit you want. But for us, we're pretty much always going to be using molarity. So it's molarity 1 times volume 1 equals molarity 2 times volume 2. And this makes sense when you break it down. So if we have the equation molarity equals moles over volume liters, okay? If I rearrange that to get M times V, MV equals moles. So imagine I have my beaker of sodium chloride again. If I dilute it, all I'm going to do is I'm going to add water to it. That's all I'm going to do. So the amount of sodium chloride in there is not going to change, right? I'm not taking out sodium chloride, I'm not adding sodium chloride. The only thing that's going to change is the volume is going to go up, and if the volume goes up, molarity has to go down with it. So the number of moles that are there to begin with has to equal the moles that we end with. So M1V1 equals the moles that we have, and we have to end with the same thing. So what we end with has to equal the same number of moles, and so M1V1 equals M2V2. If you're a math person and you can see this, great. If you're not, the equation's not that hard. M1V1 equals M2V2. In these situations, any sort of problem you're doing on a homework or a quiz or a final exam, just like any of these equation problems, you're going to be given 3 of these 4, and you just have to solve for the 4th. So they're not that hard. The only tricky thing is make sure your units are the same on the left and the right. Don't have milliliters on the left and liters on the right, or molarity on the left and molality on the right. As long as you're consistent, you'll be fine. Yeah.
It wouldn't matter. So should we always just go by the first M1V1 and then, or it doesn't really matter which one you?
It doesn't matter which one you make as 1 and 2.
Yeah.
But I think you're probably safer. You're less likely to confuse yourself if you always make the 1s the beginning,
Okay.
and then the 2s the ending. Think about the process of being in the lab and doing the dilution. Which one would you start with? Which one would you end with? So if you had a problem saying you're going to do a dilution, what was your beginning molarity? You would plug in numbers for V1, M2, and V2 to solve for M1.
Thank you.
Again, I've taken the equation and rearranged it for you, but you really need to be able to do this algebra on your own, because you're not going to be able to memorize all 4 of those things.
So those just set little divisions, like if I make V2, 1, 2, V2, 1, and at the end, 2 and 1, and the
Same
divided
here?
by each other. Yeah, is that like a division? Or?
Yes, this slash?
Yeah.
Yeah, that's division.
That was the year.
Yes, that's M2 times V2 divided by V1. So, this is an example. We have 175 milliliters of a 1.6 molar solution, and we're going to dilute it to 1 liter. We have to figure out what the new concentration of our lithium chloride solution is. So what's the equation that we need? M1V1 equals M2V2. Which of those 4 are we looking for? We're looking for M2, the new concentration. So that means we have to have M1. What is M1? 1.6 molar. We have to have V1. What is V1? 175 milliliters. And we have to have V2. What is V2? 1.0 liters. So I just plug them in. I have to convert.
It's 1.75. No, wait.
Not
It's
synchronous.
always synchronous.
It's not synchronous right now.
Or did I go the wrong way?
Right. So we either have to convert 175 milliliters to liters, or we have to convert 1.0 liters to milliliters. It doesn't matter which one we end up with, as long as they're the same. So let's convert 175 milliliters to liters. What is that? 0.175 liters. How many, if I converted 1 liter to milliliters, what is that? 1,000. So now we have everything we can plug in. We have 1.6 times 0.175 equals M2 times 1.0. So M2 equals what? 0.28. We get out the concentration that we put in. We put in molarity, so we get out molarity. Not hard, is it? If you can do gas laws, you can do this. Here's another way. These are another type of problems that you can turn all around and look at a lot of different ways. So here, we need to make 10 liters of 1.2 molar potassium nitrate. If you're going to use 2.5 liters of a solution to make that, what concentration would that have to be? This one is kind of a wacky question. So step back and look at it. Which variable is it asking you to find? It's asking you to find M1. We need to make 10.0 liters, that's a V2, of 1.2 molar KNO3. That's our M2. So then we look, we say we're going to use 2.5 liters of our beginning solution. So that is V1. The one that we're missing is M1. So we plug it in, we have M1 times V1, which is, what is V1? 2.5 liters equals, what is M2?
1.2.
1.2 molar times V2, which is 10.0 liters. So M1 equals 4.8 molar. So if you're someone who likes to check yourself, these problems lend themselves to checking pretty easily. So now you have M1, V1, multiply them together. You have M2, V2, multiply them together. If you don't get the same number for the ones and the twos, something's wrong. Here's another type of dilution problem. This is asking you to do the math, but then think about your result, which is one of those brain exploding problems, right? So, it's still a dilution problem. So it's still M1, V1 equals M2, V2. Which variable are we going to have to solve for?
Or should just multiply them all together, or well, put them where they're supposed to be and see if they're equal.
We only have, you can do that, yes. You can do that, yes. And so let's do that. So let's set them equal and see if they are. So we have 100 milliliters. So let's 100 milliliters times 3 molar. So how many moles? If we do this multiplication, we're going to get moles out. What is that? 100 times 3?
300.
We get 300. So this is this how much we have or how much we need?
That's what you mean.
This is what we need. And so we have 13 milliliters times 10 molar. What does that come out to be? 130 moles. Can we make this solution?
No.
No. So we need 300, we only have 130. That is one way that you can do this problem. And you're perfectly fine to do it that way. If that way is what makes the most sense for you. Another way you can do it is to say we need 100 times 3. So we need 100 times 3. Our starting solution is 10 molar. And figure out how much of that solution you would need to have in order to do your experiment. So when you do that, you have 100 times 3 is 300, divided by 10 is 30, V1 equals 30 milliliters. So this is saying you would have to have 30 milliliters of that starting solution in order to do your experiment. But you don't. You have 13. So there's two different ways of looking at this problem. You get to the same result in the end. Whichever one works best for you is what works best for you.
Is it valid for more questions to do it, to search for, say in that problem, to search for M2, which would be the running through with 13 milliliters times 10 molarity, dividing by your V2, find your M2, and if it's lower.
So you're saying, instead of plugging in 10 here, plug in
V1 and take away the molarity on the.
yeah, so you plug in 13 mil, basically you plug in 13 milliliters and we figure out how concentrated your stock solution would have to be.
Oh no, M2, not M1. Searching for M2, and if the molarity is lower than what you want, then you know it's not going to work.
Yeah, so you can plug in any of those three, because you actually have 4 numbers. So if you plug in any 3 of them and figure out what the 4th one would have to be, you can then think, if this is what it has to be, and this is what it actually is, what does that mean for me? It's just the thought process that goes into that is going to be a little bit different for any of the 4 that you actually solve for. So when you do these dilutions in the lab, we always have sort of a shorthand way of referring to them. And we call that a dilution factor. So this is what happens when you dilute something. This is, let's say it's Kool-Aid. You dilute it down, it's clearly getting less concentrated. It's more dilute, correct? And so we say this dilution factor is a something-fold dilution. So a 2-fold dilution means that your volume is now twice as much as it was before. If your volume is now twice as much as it was before, what is your concentration going to do? It's going to halve. Your concentration goes opposite your volume. So if you double the concentration, you have the, I think I said that wrong. If you double the volume, you are going to have your concentration. So if we say that you took this glass of Kool-Aid, you doubled the volume, and now you poured it into 2 glasses. So now this is what it looks like. And you could say that this one is twice as red as that one is. Another way you could say this is it's a 2x dilution. A 2x dilution is the same thing as a 2-fold dilution. That means that you have doubled your volume. What this is telling you the ratio between the old concentration to the new. So in a 2-fold dilution, your old concentration is twice as high as your new concentration. Does that make sense? In a 4-fold dilution, how many times more concentrated is your starting solution than your ending solution? It's 4 times. In a 5-fold dilution, what is the relationship between the volume of the starting and ending solution?
No.
We got to point out, so it's 1.
So Put it in words. Say it in a sentence, not a something to something ratio.
If you have 5 times the volume, it is 5 times more than the starting point.
Yeah. So the ending solution is 5 times more volume than the starting point. That's what a 2 times dilution or a 10 times dilution means. So if you had 100 milliliters of a solution, and I told you to do a 5-fold dilution of that, how many milliliters of water would you have? 400, not 500. A 5-fold dilution means your solution has to end up 5 times larger, right? So we're going to go from 100 to 500, but we already have 100, so we have to add 400 to get it up to 500. If we take 10 mils, dilute it to 100 mils, if you're going to tell me what dilution you did, how would you express it? It's a 10-fold dilution, or it's a 10x dilution. We now have 10 times as much volume as we started with. Okay, I think, without looking at the slides, I think this is the last idea of this lecture set. These are colligative properties. Weird word, kind of useful things. Anybody know what colligative properties are? No.
Properties of a solid suspended in the liquid.
Not suspended. Dissolved. Dissolved. So they are colligative properties, are properties that don't depend on what it is that's in your solution. All it depends on is how concentrated your solution is. Okay? When we talked about our gas laws, we said that it doesn't matter what gas you have. The last question on the quiz was, how would your answer in A change if you used air instead of helium, or something along those lines? And the answer was it wouldn't change at all, because all the gases behave the same. But you know, and with solutions, a saltwater solution is very, very different than a hydrochloric acid solution. But there are certain things, certain properties about those solutions that are going to be the same if you have a 1 molar sodium chloride solution versus a 1 molar hydrochloric acid solution. And those properties are colligative properties. And it's not just the molarity, it's how many particles are in your solution. This is one of these concepts that is incredibly simple, but some people really struggle. Okay? How many, if I have calcium chloride, if I have 1 mole of calcium chloride, how many moles of chloride atoms do I have? I have 1 mole. I have 1 mole of calcium chloride. In that 1 mole, how many atoms of chlorine do I have? How many atoms?
Chlorine?
Chlorine.
12 or 1.2 times 10 to the 4.
You can use moles as your unit.
Two.
2. Yeah. So for 1 mole of calcium chloride, you have 2 moles of chlorine atoms. Because for every calcium chloride you have, there are 2 chlorine atoms in there. So if you have 1 dozen calcium chlorides, you have 2 dozen chlorines. So if you have 1 mole of calcium chloride, you have 2 moles chlorines. With these particles, it's counting up how many total particles you get out of each one. So if you dissolve if you dissolve sodium chloride in water, how many pieces does that break into? Two. If I dissolve calcium chloride in water, how many pieces does that break into? Three. A calcium and two chlorides. So to get the number of particles in your solution, you're going to take the molarity and multiply it by however many particles you get. So if I have a 1 molar sodium chloride solution, what is the molarity of the particles in there, regardless of what type of particle they are? 2. 1 molar times 2 particles for each one, so it's sort of a 2 molar particle solution. There are 4 of these colligative properties. Osmotic pressure, which is the weird one. Vapor pressure lowering, which is not nearly as weird. Boiling point elevation, which you probably use quite often. And freezing point depression, which you may or may not have used in your life, but it's going to make sense when you hear about it. So we said that the colligative properties depend on the number of particles. And so for a problem like this, you're really only going to be dealing with strong electrolytes. Strong electrolytes, remember, are the compounds that completely break apart. If I gave you a problem with acetic acid here, remember when we did acetic acid in lab last week, was it a strong, weak, or non-electrolyte when it was concentrated? Concentrated acetic acid.
Oh, it was weak. It was neither.
There's only 3 options, and I haven't said yes yet. Which one are we missing? Non-electrolyte. The concentrated acetic acid was a non-electrolyte. When you went to your 0.1 molar acetic acid, we dissolved it in water. Now, was it a non, weak, or strong electrolyte?
I've slept since then. Do not remember that.
Wrong.
No?
Weak.
Weak.
Yeah.
So acetic acid is not an ionic compound. If it's not an ionic compound, what kind of compound is it? Molecular. Molecular compounds do not completely break apart. Only a small fraction of the molecules in your solution are actually broken apart. So it's a weak electrolyte. And so in order to figure out the colligative properties of a weak electrolyte, you're going to have to do some calculations that we don't know how to do. So for you, these colligative properties only deal with strong electrolytes. And so you can say, if I have a 1 molar sodium chloride solution, I have 2 molar concentration of particles. You can just take the molarity, multiply it by the number of particles. And the strength of these properties is proportional to the number of particles that you get out of it in your solution. So if you have 2 solutions, one has twice as many particles, these colligative properties are going to be twice as strong in that solution. What if we have a 1 molal solution of magnesium chloride? What is the concentration of ions in that solution? 3 molal. Okay? Lowercase m is molality. That's a 1.00 molal solution. So 1 times 1, 2, 3. 1 times 3 is 3 molal. So this is osmotic pressure. Osmotic pressure deals with a situation where you have two solutions of different concentration, and then there's a membrane between them. Okay? So in this situation, we have a beaker of water, and then we have an upside down funnel that's filled with a salt solution. And we put this membrane on the bottom of the funnel to keep everything from spilling out. We say it's semi-permeable because some things can get through and some things can't. In these situations, water can get through, salt cannot. In general, your solvent, which is almost always going to be water, can get through. What's dissolved in it cannot. So we put our salt solution in our water. Osmotic pressure happens because if you have two solutions that are different concentrations, they want to be the same concentration. So if instead of thinking of concentrations, we had temperatures. So imagine I had a cold thing of water and a hot funnel. And I stuck that hot funnel in the beaker. Which way is the heat going to go?
Into the glass. Towards cold.
Is it gonna go from the funnel into the water or from the water into the funnel? Funnel to water. Because they want to get to the same point. Funnel has this amount of heat, water has this amount of heat. And so as funnel comes down, the water is going to come up and eventually they're going to meet. And that's where they stop. Same thing is going to happen here. They want to be the same concentration. But instead of heat going from one to the other, water is going to go from one to the other. And so the thing with the low concentration is going to give water to the thing with the high concentration. That does two things. It dilutes the thing with the high concentration. It dilutes our salt solution. So our concentration is now coming down. It's going to get closer and closer and closer to the zero that our distilled water was. If we had, instead of just distilled water, we had a 1% salt solution. As the water goes into the funnel and this concentration goes down, our volume out here is going to decrease. So our concentration outside is going to go up as the concentration inside goes down. Yeah. That is a complicated situation, but what you really need to know is that when that water goes through, it's going to push on the membrane. Think of it like Black Friday at Walmart, okay? Everybody's crushed up against the door, and at what, 6 a.m. on Thanksgiving, the day before now, they open the doors, and everybody tries to push through. But all of that force is pushing on the doors and the walls around the door. That's the same thing that's happening here. The water wants to get in here. It's pushing and pushing and pushing, but it can only get through where there's a little pore. But the water is going to push here and here and here also. So it pushes on that membrane. So osmotic pressure is the force, the pressure that the water pushes on the membrane with, trying to get to the other side. Okay? It is actually a force. Just like if you push on it with your hand, the water is going to push on it, trying to get to the other side.
Your definition right there says the exact opposite.
Which step? Here
Pressure
or
that can
here?
be exerted on solution to prevent osmosis. You're saying it's the pressure of osmosis happening.
This is a relativity question. It's the same thing. It just depends on which way you look at it. So it is the force pushing this way. Okay? Some water is going through the pores. Some water is pushing on here. What this is saying is if you want to prevent osmosis, osmosis is the water that's actually getting through. So if you want to prevent the water from getting through, you have to push it back with the same amount of force that the water is pushing to the left. So it's the same number. It's like when you have tug of war and you have two people pulling with the same force, nothing happens. So if Zach and I are playing tug of war, I could say, well, what force am I pulling with? But if we're not moving, you could also ask, what force is he pulling with? And it's going to be the same exact number. That's this. It all depends on which side you're actually looking at. Are you looking at how much force the water is pushing with? Or are you looking at how much force you would have to push to keep the water out? It's the same number. To me, the force that the water gives is easier to visualize and conceptualize than the force needed to push back to keep the water out. Is anyone confused on this? So this is another situation where you can do that. And this is just sort of a U-shaped tube with a membrane at the very bottom, and you can load different solutions on both sides of the membrane. So in this situation, we have just water. Here we have, let's say, a sodium chloride solution. Which direction is the water going to go? From the left to the right, or the right to the left? It's going to go from the left to the right. The water goes towards the high concentration. It wants to dilute the thing that already has the higher concentration. So if you do this and you let it sit a while, you're going to end up looking like this. It's going to be this much water over here and this much solution over there. They're no longer equal. This side went down and this side went up. And so another way of looking at this osmotic pressure is if you're going to push down here, how much force would you have to push with to get them back to even? And if you look at it from the other side, that amount of force that you're pushing with is the same exact amount of force that the water is pushing on this membrane with. So we can calculate osmotic pressure. This is the equation. Okay? You're going to need this for homework, for quiz, I think.
It's not on the cheat sheet.
It's not on the cheat sheet. If you need it for the quiz, I will give it to you. What I'm trying to say is you don't have to memorize this one. Okay? There won't be a situation where you need it and I won't give it to you. Or you won't be at home where you can look it up. Okay? It looks funky. Funky is a good word for that, I think. So pi is osmotic pressure. That is a symbol for osmotic pressure. I is the number of particles that you get out of your compound. So what is the I for sodium chloride? 2. What is the I for calcium chloride? 3. What is the I for sucrose, sugar? 1. It dissolves, but it doesn't break apart. Molecular compounds don't break apart. So one molecule of sugar gives you one particle. It doesn't break apart. So when you're doing these, you always got to look at, is it an ionic compound or molecular compound? Is it going to break apart? So if I gave you benzene, C6H6, don't tell me that the I is 12. What is the I of benzene? 1. It's a molecular compound. It doesn't break apart. R is our gas constant. It's the same exact number, 0.0821. It's pressure. The same principles work with our liquids as work with our gases. T is temperature, has to be in Kelvin. Don't try it in Celsius. M is our molarity. If you combine I and M together, it's called osmolarity. And so if you calculate, then if you say, how do I do this? So say you have 1 liter of a 1 molar solution. So 1 equals moles over 1. How many moles are in that solution? 1. So if I told you that solution is sodium chloride, so you take the 1 mole times I of 2, and you're going to get 2 osmoles. You put the os when you're talking about particles. So if you want to make it simple, you can just stick with that. IM is osmolarity. I is the number of particles that you get out of each molecule. M is molarity. R is gas constant. T is temperature. You can calculate pi, which is osmotic pressure. If you want to be able to think about it, what you're actually doing, you can figure out what the heck is osmoles per liter. That's just saying it's particles instead of molecules. So where osmolarity really comes up in real life for a lot of you is osmolarity is really important in biology, in medicine. All of our cells, the plasma membrane in our cells, are semi-permeable membranes. So if we get the osmolarity of something wrong, our cells will swell up or shrink down. So if you're going to inject something into someone, especially if it's a large volume of something, you better get the osmolarity right. Otherwise, the patient may blow up like a balloon or shrivel up like a raisin. So we have to make 1.5 liters of a glucose solution that we're going to give IV to a patient. It says the osmotic pressure of blood is 7.65 atmospheres at body temperature, which is 37 degrees. How much glucose do we need to dissolve in how much water in order to make the solution that we're going to give to the patient? So let's go back to our equation. Our equation is pi equals I m r t. How are you going to start?
We got temperature.
You've got temperature. It's in Celsius, but you've got temperature. Let's start there. So T is 37 degrees Celsius, which is what in Kelvin?
Yes.
Should be, I think.
310.2.
310.15.
No, 310. Ah, that's not right. Sig figs.
Let's wait till the end for 6 days.
It's the furthest left. It's so easy. Just drop it.
Okay. So we've got T. We have R.
Yes.
Well, what is R?
0.08206.
R equals 0.
Wow. Point raisin.
0.0821. So R is 0.0821. Do we have molarity?
No.
I don't see it. So molarity is a question mark. Do we have I?
It'll be 1, right?
It's 1. Glucose, just like sucrose, table sugar, is a molecular compound. The I is 1. So I is 1. We don't have M. So if we don't have pi, we're not getting anywhere. Yeah.
So how do you get zero?
R, this is a gas constant, so it's on the cheat sheet. It's always 0.082.
Oh,
Just like when we did the PV equals nRT, if you remember that, R was 0.0821. Always. So here R is 0.0821. So we don't have M, so do we have pi?
It's not 3.15.
It is not 3.15, and it's 5, and it is not coconut cream.
Would it be 1.5?
Or mincemeat, or apple, or anything like that. What is it? Yeah, well, in this situation, what is the value of pi?
7.65 atmospheres.
7.65 atmospheres.
What?
Is it
It's
suppression?
hot. What?
It's pi, the Greek letter, right?
Greek
It's Greek.
letter.
Is pi the Greek letter? It's not pi the circle pi. We reuse letters because the Greeks have a short alphabet. So pi gets different letters, Greek letters get used all over the place. So this is not pi. This is pi. Osmotic pressure pi. So
So it's always gonna be the pressure then?
yes, so it is the pressure. And so the osmotic pressure in our solution, which is what we're putting into our equation, has to be the same as the osmotic pressure in the person. And it says, in the person, it's 7.65. So we have no choice. We have to make our solution at 7.65. So now we have everything except M. So 7.65 equals 1 times M times 0.0821 times 310.15. M equals what?
On your R, yeah, 0.3.
Is it just 0.3?
You have a sig mix.
So we're going to say our M is 0.3. So our solution has to be 0.3 molar. Is that our final answer? No. The question is asking us how much glucose should we dissolve and how much water should we dissolve it? So how the heck do we get that from that?
You need 1.5 liters.
You need 1.5 liters. So we're going to dissolve it in 1.5 liters.
But M1.
So our molarity equation is molarity, which is 0.3, equals moles over liters, which is moles divided by 1.5 liters. And so you get 0.45. You solve for moles, you get 0.45 moles. This is longer than you would.
Glucose?
Yeah. So you got 0.45 moles. We now have to convert our moles. Well, actually, no, we don't have to. It says how much. It doesn't say in grams. So we can stop here. We can say you have to dissolve 0.45 moles of glucose in how much water? It's not, there's a little nuance here. How much water do you dissolve it in? See if anybody can catch it.
Would it be 1.5?
If you add 1.5 liters of water, it's going to be too large. Because 0.45 moles of glucose is a lot of glucose.
Do 0.3.
The trick here is you add your take your glucose and you add water to it until it's 1.5 liters. And so the answer would be you dissolve 0.45 moles of glucose in sufficient water to give 1.5 liters of solution. However much that is. Unless you're in a lab, you can't figure out how much that actually is. So you say, I would dissolve it until I had 1.5 liters. So these are what happens to your blood cells if the glucose is not made right. So a normal blood cell looks like that. It's got a dimple in the middle. This is a blown up blood cell. That's a shriveled up blood cell. So if you take a blood cell and you put it in a solution, we have terms that describe that solution relative to the blood cell. An isotonic solution is the same concentration as the concentration in the blood cell. So if you have the same concentration inside as outside, everything's happy, water doesn't move, and your blood cell looks just the way it's supposed to. If you have a hypotonic solution, that means the solution you put it in is less concentrated than the blood cell starts out as. And so water is going to go into the blood cell, trying to dilute whatever is in the cell. And so your cell is going to swell up. Eventually it will blow up. It does happen. The opposite is a hypertonic solution, where you put it in a really concentrated solution. And so the water is going to come out of the cell into your beaker. And so your cell is going to shrivel up. So remember, think of a hyperspeed. It's really fast. Hyper is high, hypo is low, iso is the same. Does this make sense? So if I take that back, and I say that in a blood cell, the sodium chloride concentration is 1 molar. If I put it in a 2 molar solution of sodium chloride, what is my cell going to look like afterwards? It's going to look like C. It's a hypertonic solution. Water is going to come out of the cell. It's going to shrivel up. Somebody give me the concentration I would have to put the cell in to make it look like that. Less than 1. You could put it in pure water. You could put it in a 0.5 molar sodium chloride solution. And if you put it in a beaker of 1 molar sodium chloride, it would keep looking like that.
So it's only the heat spots on them. Heat cups.
I'm guessing that's not heat. That's probably the type of microscopy they used. It makes it look like that. It gives it depth, I would guess, why it looks like that. This is a... Let's do one more colligative property, then we'll do a break. So the next one is vapor pressure lowering. So if you dissolve something in your water, there are two different types of things that you can dissolve in. You can dissolve something that's volatile or something that's non-volatile. A volatile solute is something that easily makes a gas. A non-volatile solute is something that does not easily make a gas. This one has more examples that you can think of. What is an example of a non-volatile solute? Water. What? I would actually consider water somewhat volatile. Because if you leave water sitting on the desk, it's going to evaporate. What's something that you can leave on the desk and it doesn't evaporate?
Desk.
Your camera?
A solid, right?
So
Or our great example that we always use, sodium chloride. Sodium chloride is just going to sit there.
I swear I heard you say something for like 30 times today.
It's a great example.
He's so salty.
All that sodium chloride, you're still salty.
So if you dissolve sodium chloride in water, that sodium chloride is not going to dissolve out of it. If I put ethanol in water, ethanol is volatile. Ethanol will easily evaporate. So if I leave a solution of ethanol in water sitting on that bench, and I come back later, the ethanol is going to be gone. That is a volatile solute. And so we talked about vapor pressure before. The vapor pressure was the pressure that we get in the gas phase above our solution. So if we have a flask filled with water, and we put a cap on the top, we're going to get pressure. Some of this water is going to evaporate and form a gas up here. And it's going to form a gas until it hits that vapor pressure. And we had graphs and things that we could use to find out what the vapor pressure was at the temperature that we were at. If we dissolve something in this solution, it actually lowers the vapor pressure. So here, we have the same amount of water down here to start, and we got 6 molecules of water in the gas phase. Now we've dissolved something yellow in our solution, and now only 4 water molecules have gone into the gas phase. The way I kind of think about this is goalies. Basically, you have a solution, you have these water molecules flying around, some of them will eventually go up into the gas phase. You have these now salt particles, or whatever they are, in there. They basically get in the way. They prevent them from coming up. So they kind of sit at the top, some of them are going to be at the top, and the water molecule that was going to escape is going to hit the salt molecule and bounce back down. So it's going to prevent it from going into the gas phase. This is something that you can do at home. It's interesting. It's going to take a long time to work, but it will work. Take a closed container. You have 2 glasses. One has water. One has a concentrated sugar solution. You could also use salt. Start with the same volume in each glass. Let it sit for a long, long time. And eventually, the water is going to go from here into there. So you can make a bet with somebody at a party saying that you can transfer water from one glass to the other sitting on the other side of the room. It's going to take a long time, but it's going to do it. Because the vapor pressure here is higher than the vapor pressure over here. So more water molecules are escaping here than are escaping here. But they're going into, once they're up here, they have no preference over them. So the water vapor is going into them both at the same rate, but it's evaporating out of this one faster than it is that one. So the water comes out of here, into the gas phase, and over into that. Okay, let's take a break. We'll start at, when the little hand, when the big hand is on the 5 on that clock. colligative property is boiling point elevation. Can you think of a time that you use this in your everyday life?
Liquid velocity.
Everyday life.
When you cook.
When you cook. Were you in here when the picture popped up?
SpongeBob.
Oh, maybe, okay,
I
maybe.
mean, probably violent.
When do you use it when you cook?
Like when you're boiling water.
When you're boiling water. Boiling spaghetti. Have you ever heard of putting salt in the water before you boil your spaghetti?
I always put salt on it. It slows to a boil.
Well, it takes it longer to get to the boiling, but once it's there, it's going to boil at a higher temperature, so your pasta is going to cook faster. A lot of people think that it is for taste. If you have a giant pot of water, and you put a couple shakes of salt in there, that's not going to change the temperature, the taste. You're not going to taste that salt in your spaghetti, especially once you cover it in tomato sauce. That salt is not there for taste. It's to change the temperature of the water. So imagine you are a professional chef. Well, actually, professional chefs probably don't boil their own pasta. You're the sous chef for the person who makes a lot of money. You're boiling that person's water. And your job is to keep making their pasta. You don't want to wait longer to cook your spaghetti than you have to. So if you put salt in your water, it's going to take longer to boil. Because instead of boiling at 212 Fahrenheit, maybe now it's going to boil at 250. So it's going to take longer to get to boiling. But now you're putting your spaghetti in the 250 degree water instead of 212 degree water, and your spaghetti is going to cook faster. So if we go back, not only does the solute change the vapor pressure, it also changes the boiling point. And the boiling point and the vapor pressure are very, very closely related. They both have to do with the liquid becoming gas. You can more kind of think of these two colligative properties as more or less the same thing. But here we've separated them into two different things. So when you add a solute into a solvent, like salt in the water, you raise the boiling point. And it's a pretty simple little calculation. M, lowercase m, is molality, and Kb is a constant value for that solvent that you multiply your molality by. And so if you're adding something to water, it doesn't matter whether you're adding salt or ethanol or glucose or sucrose, it's still water, so the value of K is the same. So you take that value of K, you multiply it by the molality of your solution, and that tells you how much your temperature changes by. That's delta T boiling point. That's the change in your boiling point. So if you have a 1 molal solution, and I tell you that the value of K for water is 2, by how much does your boiling point change? 2. 2 times 1, the delta T is 2. So the boiling point of water has gone up 2 degrees. It's not complicated. You know how to calculate molality? Kb has to be given to you. Multiply the two together, and you get your change in temperature. The last one to look at is freezing point depression. Can you think of a situation where you use freezing point depression in a regular life?
Ice cubes.
But what about ice cubes?
Ice tray.
How do you use freezing point depression in ice cube trays?
You're lowering the freezing point, or not freezing,
What if you look at it, melt the ice?
Yes. Yes. So I think the only person who ever raises their hands when I ask if anybody grew up north is Kim, and she's not here. Anybody grew up north? in the snow, in the ice.
So just spend time with them, aren't they?
Well, you Tennessee, they probably put salt in the road in Tennessee, don't they?
Probably a couple times a year.
Yeah, but you know that they do that. And so the idea is, if you put salt on the road, you lower the freezing point, you depress the freezing point of that water. So now the water freezes at a temperature below the outside temperature. So what's the freezing point of water in Fahrenheit? 32 degrees. So if you get pure water on a road and it gets to be 30 degrees, it's going to freeze. And you get ice on the road. But if you put salt on the road, now that water freezes at maybe 25 degrees. But it's only 30 degrees outside. So your water's not going to freeze and you just have a wet road instead of icy road. It's the same calculation. Molality times a heat constant. This is the freezing constant. It's Kf instead of Kb. But you then get delta T. So if K is 2, the molality is 1, your freezing point is going to go down by 2 degrees. That's all there is to it. So I don't think you even ever have to do calculations like this. What you need to know is what happens to the freezing point when you increase the concentration of the solution. Does it go up or does it go down? It's going to go down. It's freezing point depression. So as you increase the concentration, the freezing point will go down. It was boiling point elevation. So as you increase the concentration, the boiling point goes up. So this is salt going on the road. Yeah, question?
There was another tip I was curious of, I guess, with an ice cream machine of putting, was it like rock salt or something out in the ice?
Yep. So if you've ever made ice cream, either an ice cream maker, a hand ice cream maker, or you can actually do it in Ziploc bags. I've done that too. You put salt in water. Actually, next time you go in the lab on Thursday, sitting on top of that flammable, yellow flammable cabinet, when you walk in, there's been a big box of salt, and it actually says ice cream salt on it. So you can see that next time. What that does, if you take ice and you put salt in it, it's going to lower the freezing point. So if you take ice and you put it as pure ice, and it starts to melt, what temperature is that ice going to be? Without salt. At what temperature does ice melt? 32 degrees Fahrenheit. If you add salt to it, is the freezing or melting point going to go up or down? It's going to go down. So now if you take that same ice and you add salt, when it's melting, it's going to be at a lower temperature. So now you can get a colder temperature around the ice cream that you're making. If you just put ice around it, your ice cream is going to be 32 degrees. If you put salt in it, now maybe you can get your ice cream down to 25 degrees. So that helps you to make and solidify your ice cream. Same exact thing happens in another situation. When you think of another situation, you might do this. I don't know if any of you do this. This was on Mythbusters once, where you add ice to salt for another reason.
Cooling down drinks.
Cooling down drinks. If you put ice into a cooler of salt into a cooler of ice, the ice in that cooler, in the water down at the bottom, is going to be colder than it would be if you didn't add salt. So the drinks in the cooler are going to get cold faster, and not only that, they're going to get colder. Instead of being 32 degrees, maybe they'll be 25 degrees.
I actually saw that it said Mythbusters.
Did you?
It's an idea.
That was one of the original ones a long time ago.
Then they use a fire extinguisher to put on the beer.
What was it?
Make them kind of frosty with it, kind of freeze.
I don't know what temperature they freeze it at. There's a lot of stuff dissolved in there.
Yeah.
So the freezing point of the soda is probably really low. So, we have three solutions. Three different things dissolved in there, or looks like two different things. These two have different concentrations. So it says which solution would have the highest boiling point? Somebody said B. Somebody said B. Anybody say A? Anybody say C? Does anybody other than Alkmaar say B? Got two.
Definitely not C.
Okay.
B. The next one, A is a spoiler.
Yeah. No, I take my vote back, I say B.
Does anybody say something other than B?
Don't do it.
It's B. So, think about it. It's the highest boiling point. So, when you add something to a solution, does the boiling point go up or does it go down? It's going to go up. So the one with the highest boiling point is going to be the one that went up the most. So the one that went up the most is going to be the one that had the highest concentration. And now, you can't just look at the molarity. Why can't you just look at the molarity of those three and pick the one that's the highest?
This one's molecular compound.
One's a molecular compound, one's ionic. And so it's the osmolarity that matters, not the molarity. So this one, you get two particles on it. So the osmolarity of that is 0.4. It's higher than that one, but it's still lower than that one. This one has the most particles. Visually, you can just count. This one has 4, that one has 5, that one has 3. The one with the most particles will have the most elevated boiling point, so it'll have the highest boiling point. Which one will have the lowest freezing point? Got an A, a B, and a C. Anybody for E? E? So somebody explain to me why their answer is correct.
You add more shape, you get a lower freezing temperature. B.
Yes, but we use particles. or osmoles. You can make, there are plenty of weird words in science. You can make your own profanity. People won't know what you're talking about. They'll just assume it's profane. If we're dealing with freezing point, the freezing point is freezing point depression, right? So when you add particles, the freezing point is going to go down. So the one that has the lowest freezing point is going to go down the furthest. So it's the one that has the most particles in it. So it is B again. You can probably see this looks it's like the same type of problem as those stupid what were they? Specific heat problems, where it gave you a chart and it said which one has the highest temperature, which one has the lowest temperature, and it depends on whether you're going up or down to begin with, which one you pick. So you really have to read the question, because if this one said which should have the highest freezing point, which one is it? It's C. Because this one has 4 particles, this one has 3, that one has 5. The one with the highest freezing point is the one that changed the least. And the one that changed the least is the one with the least number of particles. So here we have 3 more solutions, but there's no pictures to count. So it says, which one will have the lowest freezing point?
The first one?
So I hear some for this one, some for that one. Anybody for this one? Got one for KBR. First one and the second one.
But the first one has,
It's gonna be
Why B?
Because CH3CH2OH is just gonna be 1,
Right.
so it's gonna be 0.5, and
Right.
then CA is,
This is molecular.
yeah.
So you only get one particle. So your osmolarity is 0.5. 0.5 times 1 is 0.5. How many particles do you get out of this?
1 mole.
You get 3 out of that. So 0.5 times 3 is 1.5. How many particles do you get out of that? 2. 0.5 times 2 is 1. So the lowest freezing point is the one that has the most particles, which is this one. So if I gave you those 3 and said which one has the lowest boiling point, which one is it?
Cha-cha-cha.
I don't know, the top one.
Cha cha cha. This one has the lowest number of particles. So the boiling point is going to change the least. So it's not going to go up very much. So it's going to have the lowest. So they're not complicated. They have elevation and depression right in the names. You just have to stop and think about which way you're going, and is that going to be the lowest concentration or the highest? The highest concentration will change the most, always. Okay. Questions on that? Okay. Time to go over homework questions.
Those are next week, right?
Yes, they're due next week. We can go over the ones that are on this quiz.
Isn't that the last, like,
74, 75, 76. Just 3, I guess.
those are equivalent in the question?
Yeah, they're. But we'll talk about it once we get
Can't be 3 questions.
there. But if there's 3 and you get one wrong, because.
No, that's true.
So, which of these is a suspension?
Great. Muddy water.
Muddy water.
Why?
A suspension has visible particles in it, and if you let it sit, it's going to separate out. So if you have grape juice, and you let it sit there, it's going to stay the same. So if you have muddy water, and you let it sit there, the mud's going to settle out. Right? What would you consider grape juice? What would you call that? I'll say there are no particles. There are no large undissolved particles in grape juice. So what would you call it? It's a solution. What would you call air? I'll tell you, air is a solution, a colloid, or a suspension. It's one of those 3. Which one is it?
Solution.
Air is a solution. There's oxygen and argon and all kinds of stuff in with a whole bunch of nitrogen. So you can think of it as a solution, a nitrogen solution that has other gases dissolved in it. You want to dissolve potassium chloride. At which of these temperatures is it going to be most soluble? Why is it 40?
Like the warmer something gets, the easier it is to develop,
Right.
with the exception of salt.
Correct. Solids. That only works for solids. What about gases?
It's the other way around.
It's the other way around. Gases are more soluble in the low temperature one. Read the question. So, 76. Somebody want to come up with 76? Nobody? Thank you. For what?
For sodium chloride.
Sodium chloride is 58. So you got ones up there, right? Yeah.
Yeah.
So he just took his grams, he converted his grams into moles. He took his milliliters, converted them to liters. And 175 milliliters is 0.975 liters. And then just took 0.17 divided by 0.975, you got 0.174. Okay. Questions about those three?
Number 51.
Say it
What's the
again.
number 8 to 10 for what he wrote?
That? 58. Molar mass of sodium chloride.